Okay. Hi, everyone. We are starting with the oral session number 1 in a few minutes.
Okay.
This space is big enough for stuff because in principle, actually, they should be very strict about when you do it.
Hello, everyone. Please take a seat. We're getting started with this session. So welcome, everyone. We are chairing the session. This is Vikash Kumar from CMU. My name is Jeanette Boak from Stanford University. And we are starting the session with a talk by Dian Wang on equivariant diffusion policy. Thank you.
Thanks, Jeanette, for the introduction. Hello, everyone. I'm Dian Wang from Northeastern University. It is my great pleasure to be the very first oral speaker at CoRL 24, and I'm very excited to share some of our recent works on equivariant diffusion policy. This work is a collaboration between Northeastern and the Boston Dynamics AI Institute, and part of the work was done during my internship at the institute. Recently, diffusion policy has been quite successful in manipulation behavioral cloning because it can well capture the multimodal distribution in human demonstration data. However, one of the problems of diffusion policies is that we need to learn a denoising function, which is a mapping from the observation, noisy action, denoising step K, to the noise prediction output. Compared to a standard policy learning framework, which is simply mapping from observation to action, this is a significantly larger function space to learn. Thus, it is typically requiring more data and time to train. So if you have ever trained a diffusion policy yourself, you might have noticed that although at the end of the training process, it can give you very good, smooth trajectories, but it typically requires more data and training time. So this poses a key question: how can we improve the learning efficiency of diffusion policy? So in this work, we propose to leverage the symmetric or equivariant properties in the diffusion denoising process to improve diffusion policy. Let me first introduce this idea with an illustrative example. Let's consider a letter alignment task where we need to drag the I letter to align with the A letter. In diffusion policy, we're going to start from a randomly sampled trajectory and then iteratively apply a sequence of denoising process until we have a smooth trajectory at the end of the denoising process. So now if the robot is in a different state where everything is rotated, what we want here is that ideally all of the intermediate states in the denoising process should be rotated accordingly, so that at the end of the denoising process, we will have the exact same good trajectory as before, but in a rotated context. Formally, given this noise prediction function epsilon, we can prove that whenever we are learning a policy that is equivariant, this noise prediction function should be equivariant as well. That means if we apply the same rotation to the input observation and noisy action, we want the output noise to rotate accordingly so that the entire denoising process is equivariant. The main contribution of this work is that we enforce the symmetry inside the noise prediction network so that we don't need to learn from the different rotated versions of the same observation and noisy action pair. Thus, we can dramatically improve the sample efficiency or learning efficiency because we can automatically generalize over symmetries. So in order to do this using IQR neural networks, we need to answer the question about how a rotation is going to apply to the observation and noisy action. So the group operation or rotation on the observation O is relatively easy to model. It can be just simply a rotation of the vision features like image or voxel grid, but how does the rotation apply to action is less clear. So in this work, we study how an SO2 symmetry operates in an SE3 gripper action space. So we're going to consider both the absolute action space and the relative action space. So here, I'm going to briefly talk about the absolute action space. Please come to me the poster or refer to the paper for the relative action space. Consider action A. That is a 4x4 transformation matrix representing an SE3 target pose for the gripper. We can further define another transformation matrix TG that is corresponding to the rotation G around the z-axis of the world. So the group operation of G on A can be further written as a matrix multiplication between TG and A, right? So based on the rule of matrix multiplication, we can further write this down as applying the 2x2 rotation matrix R to the top 2 rows of the action A, while leaving the other 2 rows of A unchanged. Because the last row of the transformation matrix is constant, we can further define the action as a set of 4 different vectors and 4 invariant scalars. When there's a rotation in the world, we want those 4 vectors to rotate accordingly, and we want those 4 invariant scalars to remain unchanged. So that way, we can define the rotation operation on the action space, and then we can go ahead and implement this using an equivalent neural network. The equivalent backbone that we use here is called Steerable-Thin, developed by Chelsea et al. So for more information about the network, please refer to our paper. We first evaluate our equivalent diffusion policy in the mimic-gen domains. It contains 12 different robotic manipulation environments, including simple tasks like block stacking to challenging tasks like coffee preparation. We consider 2 different versions of our method, one using voxel input, another using image input. We compare both versions of our method against 3 different baselines: the original diffusion policy, the 3D diffusion policy, and the action trunking transformer used in Aloha. On the left table, we show the performance comparison when all the methods are trained with 100 demos. We can see that both versions of our model are outperforming the baselines, while the voxel version of our model is achieving a roughly 20% improvement across the board. We further consider increasing the number of demos. On the right table, we show the average performance across all 12 different environments, but we consider 100, 200, and 1,000 demos. We can see here that our model trained with 200 demos is outperforming all of the baselines trained with 1,000 demos, representing a 5-fold improvement in sample efficiency. We further try to study where the symmetry in our network helps the most. We categorize all of the tasks into 3 different groups: the high equivalent group, where all of the objects are initialized more randomly, and then we also consider mid equivalent group and low equivalent group, where there are less randomness in the initial distribution of the objects. Because of the symmetry in our model, theoretically, we should get the best performance in the high equivalent groups. On the right, we show the performance difference comparing our method and the vanilla diffusion policy. So we can see that as we thought, we're going to have a better improvement in the blue high equivalent groups. But what is worth mentioning is that even though we are in those mid and low equivalent groups, we still get a performance boost, especially when we have 100 demo in this low data regime. That represents the robustness of our method in partially symmetric tasks. We further perform several robot experiments, including a very complex bagel baking task, where the robot needs to open the oven door, pull out the oven tray, pick up the bagel, put the bagel on top of the tray, and then close the oven door. It is a very long time horizon task, but we were able to train a successful policy using only 58 demonstrations. We also consider some other tasks, where all of them can be trained within 60 demonstrations. In the end, we consider a generalization experiment where we, during training, we only initialize the O1 in 3 different orientations. But during testing, we randomly orient the O1 inside the workspace. We can see that even though those random orientations are never seen during training, because of the symmetry in our model, you can generalize to those orientations directly. Thank you so much for your attention. Please visit our website or scan the QR code for the paper code and other materials. We will also have a poster at the poster session 2, and please feel free to stop by or shoot me an email if you have any questions. Thank you so much.
There's a question over there.
No.
Testing? Okay. First of all, hello, Dian. Thanks for the great presentation. I was wondering if you had any insights, or did you do any experiments sort of looking at the, I guess, like the discrepancy between state and observation equivariance? The formulation for a lot of these equivariance policy frameworks is always with respect to the state of the scene, but obviously when you design the policy, you only have access to, for example, a point cloud observation or an RGB render. So there's a bit of a mismatch there. Do you have any insights into that?
Thanks, Laura. This is a great question. So recall that we had 2 different versions of our model, one using voxel input, another using image input. Part of the reason is exactly because of that. So whenever we have a voxel or point cloud, like a more complete representation, this symmetry on the observation space can be more well captured. But if you have, let's say, a third-person view image representation, there is going to be a larger gap between the actual rotation you can apply in the observation space compared to the ground truth orientation in the state space. But we actually had a prior work before studying this problem, and we discovered that even though we have this symmetry mismatch between the observation and the ground truth rotation, we still can have a significant performance boost by using the equivariant models. But if you have access to a more complete observation, like voxel or point cloud, we're going to have better performance.
Thanks.
Let's thank the speaker again.
Unless you want to use.
I think anyone is fine.
I trade you.
Okay. Hello. Can we get the slides up over here? All right, perfect. All right, our second talk is going to be D-cube fields by Yunzu Li. Yunzu?
Okay, really great to be here. I'm Yunzu Li. I'm currently here to present our work on D-cube fields, dynamic 3D descriptor fields for zero-shot generalizable rearrangement. This is a joint work with Yixuan, Mingtong, Zhuoran, Tarek, Katie, Jiajun, and Feifei. So in this work, the key questions we hope to answer is what should be the right representations we use for robotic manipulations. Looking at these videos of how humans organizing the shoes on the shoe rack, it involves some dynamic movements of the shoe, and the movement is also in the 3D space. And if you look at how humans are placing the shoes, they're not placing the shoe in a random manner. They're actually aligning the shoes according to their shoe tips. That means the representation will also have to contain semantic information about this environment. So there has been a lot of great work recently in the vision communities in developing visual foundation models. They show surprisingly generalizable capabilities in a range of tasks like segmentations or learning pixel-aligned visual descriptors. But none of them are actually in the 3D space, and there's still a step we need to take in order to ground these informations for robotic tasks. So in this work, we propose D-cube fields. It is a scene representation that is simultaneously 3D, semantic, and dynamic. And the key things we want to highlight is that it only requires sparse viewpoints, like 2 views, 3 views, 4 views, and it requires no training and distillation at all. So specifically, here's how the system works. Given the scene, like 3 shoes, we have multi-view visual observations of these environments. And each view will be fed through these foundational vision models like grounded SAMPs or DynoV2. And then for arbitrary 3D locations in the 3D space, we will project that 3D locations into the corresponding locations in the input images and be able to obtain the information from those foundation models. And then this is essentially a neural field representations of the environments. And we can do marching cubes on top of that, which will essentially give us reconstructions. Reconstructions of both the geometry and the semantics. And semantics, what I mean here, are actually semantics at different levels of abstractions. In the third columns, it is actually semantics indicating the object instances. And on the right, what we are showing are semantics at a more fine-grained level of describing objects in their part level. So essentially, the color here, meaning how close they are, is the closer the color, the closer they are in this kind of semantic measurement space. And you can measure, for example, the similarities of semantics and also the similarities of different object parts. We can do some very interesting experiments. Here, we take an image of our table, which contains a mark. On the right are actually images taken from the data sets from dense object nets. So we can hover our mouse on the query image, and we can query the informations in our target environments to see what are the areas in the target environments that are similar to the query image. And if the query point is on the bar, you're able to see like the highlighted areas in the bar parts in the target environments. Like here, the correspondence is really been doing in the 3D space. And in the middle columns, we are essentially project the 3D correspondence in the 2D image for better illustrations. And if you move the points in the rim areas of the mark, the rim will actually also light up in the target environments. Here's another example. If you move the points in the bar parts of a fork, the bar parts in the target environments will also show up for different utensils. You can see here is actually generalizations of course simulations and the real environments, where the target environment actually in simulations. And here's what's interesting. As soon as you place the points in the head part of this fork, only fork parts in the target environment has been light up, which indicates some very interesting fine-grained semantic understanding about these environments. Similarly, if you place a point on the bar part of a knife, all the bars will light up, but as soon as you place a point on the head part of this knife, only the knife head will be light up in the target environments. And obviously, if you can measure the similarities of semantics over the spatial level, you can also build the correspondence at the temporal level for dynamic modeling of these environments. So given these representations, we are trying to use these representations for planning. For example, given the current environments and the target image we hope to achieve, here the image is actually an AI-generated image. We'll map the environment into the 3D descriptor fields, and the goal image will also be mapped into this 2D descriptor fields as the same like descriptor space. And then we'll define the correspondence between our current environments and the target image. And the correspondence of different parts of these two environments will be used as the loss for us to do planning. And we have evaluated our systems on a range of objects shown on the left, and different types of target images shown on the right, is including like both simulated image, real images, AI-generated images, or even like human sketches. And for example, given the target image, we'll be able to like plan the robot's behavior and reorganize the tables into achieving the target configurations. One thing to note here is that the background is different, and the instances we are manipulating are also different from the target image. Here are just some more examples where the robots will be able to like understand like whether the knife is on the left or a spoon is on the left, trying to reorganize the tables according to the target image. And here are just some more examples. Here on the left, we actually show real-world target image. And on the right, what we're showing are actually the robot executions in simulations. This shows some very interesting generalizations between simulations and the real world, where the robot will be able to rearrange the environments according to the image specified as a target. Here's another examples where the robots are actually using two Go images to specify some more compositional to use a more compositional ways of specifying the targets. Here, if you use our representation together with a nerd dynamics model, you'll also be able to do like model-based planning of like gathering like granular pieces or push the shoes to align with the target configurations. And this is actually a follow-up of our representations, in which we are actually also using the representation for imitation learnings. You can see that our representation can provide category-level generalizations. So we'll also train our policies by collecting data, for example, only on 2 spoons. Here we are actually grabbing the spoons and trying to scoop some coffee beans into the cup. And by collecting data only on 2 spoons, you'll actually be able to generalize, of course, different shapes of spoons. The robot will realize what are the semantically parts corresponding to the grasping, and what are the semantically parts that are corresponding to the scooping actions. And this representation can also help us highlight some nuanced visual features in the environment. Here the task is actually to place the Coke can into the upright position. But it's actually really hard to, just from the visual RGB informations, to realize where the lid of this can is. So our representation can help us highlight the task relevant regions of these objects and be able to place this Coke can into the upright position correctly. This also can be extended to other tasks. For example, here the task is trying to align the head of the toothbrush with the toothpaste. Our representation is successfully in highlighting, for example, the head of the toothbrush and be able to align the head of the toothbrush with the toothpaste and be able to accomplish this task. So to summary, this is essentially a work that leverages the structures of neural fields, where the neural fields contains simultaneously 3D, semantic, and dynamic informations. It allows us to do the reconstructions using only sparse views and requires no training and distillation at all. It supports generalization across instances within a category. It can also generalize across sim and real instances and contexts of different variations, as well as to AI-generated image. And when you use this representation for model-based planning, it allows flexible goal specification, and if you use it for imitation learning, not only it supports category-level generalizations, it can also review fine-grained visual cues in the environment for you to do manipulations. So in the end, I would like to thank all my collaborators in this work. Without them, it would be impossible to do all of this work. Specifically highlights to Yixuan, Mingtong, and Zhou Yang, who is leading this work. So yeah, that's the end of my talk. Happy to take any questions.
There should be 3 microphones. You can raise your hand. One over there.
Hello. Thanks for the exciting talk. It's really, really amazing. I was wondering how is performance on cross-object manipulation? What I mean is that in the demonstration video or picture, there are some objects, but they are not existed in the reality, and what the robot will do in these cases.
Yes. So essentially, because our model leverages visual foundation model, specifically DynoV2, DynoV2 can actually provide some very interesting coarse instance correspondence for objects that share some semantic similarities. For example, the wing of a plane as well as the wing of, for example, an eagle. So in that case, it can provide this kind of very fine-grained and interesting semantic correspondence. So that's why in our case, even if the target image is an AI-generated image that would never exist in the real world, you can still find some meaningful correspondence for you to use as a planning objective.
Anyone else? I have a quick question. Is there a way to extend this to exploit semantic understanding between functional spaces, right? Like different handle types, but it's still handles, right? It looks visually very different. Do you have any ideas?
Yeah, that's a very good question. Like I showed earlier to show the highlight of the correspondence. So the robot will be able to realize if you query the handle in the query image, all the handles in the target image has been highlighted. That indicates some like semantic or even functional understanding about, okay, oh, those handles are actually sharing some similar functionalities. But as soon as you move the point, the query points, into the head part of the fork or knife, only the knife head and the fork head has been lighted up. That means they afford different type of functionalities when you actually use them. So this type of generalization is quite interesting, and obviously it requires some more systematic evaluations to really concretely making claims on how well it can do functional level generalization. But currently we have seen some very interesting initial results. Thank you.
Let's thank the speaker one more time. All right, perfect. Our third and the final talk is going to be on retrieval-based affordance transfer for generalizable zero-shot robot manipulation by Yuzhuan Kwang.
Okay. Hello, everyone. I'm Yuzhuan Kwang, a senior undergrad from Peking University. Today, I'm happy to share our recent work, RAM, retrieval-based affordance transfer for generalizable zero-shot robotic manipulation. Manipulating unseen objects in unseen environments with unseen embodiments is a long-standing goal for robotic manipulation. A traditional approach is to learn these manipulation skills from in-domain demonstrations. However, these methods are costly and labor-intensive, requiring significant human labor and prior knowledge, leading to data scarcity and generalization issues under unseen scenarios. Therefore, in this work, we aim to acquire versatile manipulation capabilities from diverse out-of-domain data. This out-of-domain data can come from many different sources, ranging from robotic data in the real world of simulation, human-object interaction data, internet-scale videos, AI-generated videos, and even cartoon or sketches. This data contain rich, actionable knowledge that are very useful to learn manipulation skills. However, they are often very noisy and heterogeneous, which means that they have very different observation and action space. Therefore, we need to rethink about how to unify and utilize such actionable knowledge in this data. To that end, we identify that the key is to represent such knowledge as a transferable, unified affordance representation. It includes where to act, which is a contact point, and how to act, which is a post-contact direction. It is object-centric because it's applicable to any data source. It's also embodiment agnostic because it can be executed by various end effectors like parallel grippers or suction cups. So, assume we have constructed an affordance memory by scalably extracting the unified affordance from diverse sources of data. But given the robot's observation and language instruction, how can we best utilize such affordance memory? Of course, we can train affordance prediction model like many previous work did. However, they are facing several issues. First, it's data inefficient, since it requires a huge amount of data and also compute to train. It's also not configurable because if an object has some novel usage, the model may not be able to adapt. And they also suffer from severe domain generalization issues under unseen scenarios. Therefore, we leverage a retrieve and transfer paradigm that first retrieves the most similar entry from the memory, and then transfers the affordance from the source domain to our target domain in a zero-shot manner. Therefore, we can overcome domain-specific hurdles and data scarcity. But how can we do it? Well, recently, the fast development of generalizable vision foundation models trained on enormous internet images offer us a solution to seamlessly connect these diverse data domains with our target domain. As shown in these figures, the emergent dense correspondence of VFM feature maps contain rich semantic information to achieve cross-domain instance and category generalization for both retrieval and transfer. Therefore, our framework can be overviewed like this. Given a language instruction and the RGBD observation, our RAM hierarchically retrieves the most similar demonstration from the affordance memory. Then RAM transfers this out-of-domain 2D affordance to our target domain and leaves it to 3D. This 3D affordance is directly executed by off-the-shelf graph generators and motion planners. Then boom, the drawer is open. In this way, we can acquire versatile manipulation capabilities from diverse out-of-domain data, leveraging a retrieve and transfer paradigm. Diving into details, our affordance memory is constructed from robotic data, which is from JOY datasets, HI data, which is from HI4D, and our self-collected custom data. We extract affordance from this data by their proprioceptive annotations, hand object segmentation model, etc., to make the affordance memory built semi-automatically with minimal human intervention. Then, given the observation and language instruction, we propose a hierarchical retrieval pipeline to retrieve the most similar demonstration from the memory, both semantically and geometrically. First, given the instruction, the task retrieval first retrieves the correct task from the memory, and then the semantic filtering filter out low-quality demos that are due to semantic mismatch or low-light scenarios. And finally, the geometrical retrieval uses stable diffusion maps to retrieve the best demonstration that has the most similar viewpoints to enable more accurate affordance transfer. After retrieval, we use stable diffusion feature maps again to do 2D contact point and post-contact direction transfer. Then, the transferred 2D affordance is lifted to 3D using a sampling-based strategy. This 3D affordance is directly executed by off-the-shelf graph generators and motion planners. We conduct experiments in sim and real on diverse manipulation tasks and compare against various baselines, including affordance prediction-based where-to-act and VRB, and retrieval-based robo-ABC. Quantitative and qualitative results show our method outperform all the baselines, thanks to our more advanced hierarchical retrieval and out-of-domain generalizability, which those affordance prediction models often lack of. On the right, we also show that our method produces more reliable affordances than baselines. Ablation studies also verify our framework design in the perspective of module design, cross-task generalization, and VFM features. Moreover, we show our method is data efficient, since 50% of the data can achieve comparable results to the full pipeline. We also show real robot demonstrations. As we can see, the retrieved out-domain demonstration from our affordance memory is shown on the top right. We also show that our method have various downstream applications. First, our framework can be used for policy distillation. The non-zero success rate can enable autonomous data collection via trial and error in a very short time. Those data can be distilled into an end-to-end policy network like diffusion policy, ACT, or VLA. So it offers us huge potential for automatic and scalable high-quality data collection for policy learning. Also, our framework is naturally adaptable for one-shot visual imitation for better controllability. It caters to specific human preference and bridges the gray domain gap. For example, our RAM can imitate the given human demonstration to either pick up the tissue paper or the tissue box. Notably, we show our method is able to bridge the gray domain gap between the real world and cartoon images like Tom and Jerry here. Moreover, our framework can integrate LM or VLM for open instructions and long horizon tasks. Similar to RAG in LMs, our method can be seen as a RAG module in robotics to enable an agentic robotic workflow. So here is the takeaway messages. We offer a retrieval-based affordance transfer framework for zero-shot robotic manipulation, a scalable manner for extracting unified affordance representation from diverse out-domain heterogeneous data, and a variety of intriguing downstream applications. So that's all for my presentation. Thank you for your listening. Now I'm open for questions. And you can also find my poster tomorrow.
Thanks for the interesting talk. I'm probably going to ask a stupid question, but I was wondering how the action is exactly mapped from the video to the robot, the action itself.
Okay, so I assume you're asking about affordance extraction. So for different data sources, we employ different strategies. Like for robotic data, we already have these n factors positions in Cartesian space using their provided annotation because we have the proprioceptive information. So we can project those 3D Cartesian positions into 2D image plane. And like for hand-object interaction data, we can use hand-object segmentation models to map the contact point and the post-contact direction. And then we can transfer such affordance to our observation and lift it to 3D and then execute it.
So what you are saying is for different types of tasks, control tasks, you have different types of control script to doing the action.
No. The control script for our observation is unified, but we employ different strategies to extract affordance from different sources of data, and they are together in a form of affordance memory. Yeah.
Okay, thank you.
All right, if there are no more questions, please join me in thanking all the speakers one more time before we close the session. All right, thank you, everyone.
I guess it's lunch now, right? Like, and there's lunch provided somewhere?
Lunch is provided in the
And then
session.
2 p.m. it starts.
Come back at 2 o'clock, yep.
Yeah. Just a quick announcement, there will be lunch provided now, as Majid has mentioned in the welcome or in the opening session. And please come back at 2 p.m. for our first early career keynote.